In this video, we're going to cover part of section 6.1, which is functions of two variables and partial derivatives. We're going to start with the definition. A function of two variables is a rule that assigns exactly one output number to each input pair, x, y. The function name is typically f, and we write z equals f of x, y. The pair x, y is called the input. The number z is called the output. For our first example, we want to consider this function in two variables. We were asked to find f of 0, 1 and f of 1, 1. So we are going to be inputting the point 0, 1, where x will be 0 and y will be 1, and then we will do the same thing for our second input pair. So to find f of 0, 1, everywhere I see an x, I'm going to replace it with 0. Everywhere I see a y, I'm going to replace it with 1. Now that I've plugged in 0 and 1, I can continue the arithmetic. This first term will be 0. The second term will also be 0. And then I will have e to the 0. Any number or variable to the 0 power is just 1. So that is my output number for my input pair of 0, 1. I'm going to repeat the same thing now with just 1, 1. Everywhere I see an x, I'll replace it with 1. Everywhere I see a y, I will also replace it with 1. This first term is 3. The second term is 2. And then the last one is just e to the first power. If I combine like terms, this is 5 plus e. Now, let's move on to partial derivatives. The partial derivative of a function f of two variables is the derivative of f with respect to one of its variables. So let's again consider this function z equals f of xy to be a function of f in two variables, x and y. If we want to do the partial derivative of f with respect to x, we take the derivative of our function f, obtained by treating x as the variable and considering y as a constant. So here are some notations that you will see for the partial derivative of f. We have f of x, or f subscript x, f subscript x of x, y, and then a bunch of other notations indicating partial derivative. If we want to take the partial derivative of f with respect to y, this time we are treating y as the variable and x as a constant. You will see very similar notations for the partial derivative of f with respect to y. Now we have a couple of notes to go along with the partial derivatives. The curly d symbol is read as partial. So for instance, if we have this notation, this is read as partial z over partial x. So you are taking the derivative or the partial derivative of z with respect to x. For our second note, notice in both of these notations for respect to x and respect to y, we are not using the prime notation. It doesn't give us enough information. If we just have a prime, we don't know if we're taking it with respect to x or with respect to y. So when we're doing partial derivatives, we do not use the prime notation. And then the last note, the partial derivative at a point, a comma b, is denoted by appending this after the partial derivative. So essentially what that means is after we take the partial derivative with either respect to x or y, and we want to evaluate it at a point, that is the notation that we would use. Okay. Let's move on to example 2. Find the partial derivatives of cxy, and that function is 6x plus 5y. So if we want to find the partial derivative with respect to x, then we treat x as the variable and y as a constant. So when we move on to finding the derivative, if we are treating y as a constant, well, 5 times a constant is a constant itself. So if y is a constant, the derivative of a constant is 0. So I essentially am not looking at the 5y at all anymore because the derivative of that will be 0. So I just now need to take the derivative of 6x, which is 6. For the second part, if I'm finding the partial derivative with respect to y, then of course y is treated as the variable, and this time x is the constant. So if x is a constant, 6x itself is just a constant. The derivative of a constant is 0, so I only need to take the derivative of 5y. The derivative of that is going to be 5. So this is just a very basic example getting us used to when we're finding the partial derivative, which variable we treat as a constant and which one are we treating as an actual variable. Now let's get into some more examples. Example 3, we are finding fx and fy for each of these 3 functions. So we're going to find the partial derivative with respect to x. We're going to find the partial derivative with respect to y. I'll start with the partial derivative with respect to x first. So keep in mind, if I'm finding the derivative or partial derivative with respect to x, I am treating y as a constant. All right, so let's go ahead and look at this first term. When I'm taking partial derivatives, I like to write my constants first. So if I'm taking the derivative of that highlighted term, y is a constant, so I'm going to go ahead and write it first. And then what's left is for me to take the derivative of x squared. Well, the derivative of x squared is 2x. Okay, I'm going to repeat this process. If I want to take the derivative of my next term with respect to x, I do this the same way we always have been doing it because there's no y here. This will just be plus 3. If I want to take the derivative of this term with respect to x, notice there are no x terms at all. Y is a constant. So if I have some number cubed times -4, it's just going to be some number. The derivative of any number is 0. So essentially this is almost like plus 0 because the derivative of that last term is 0. Now I am going to clean this up a bit. For the purposes of this video and the activity that goes along with it, please write your letters in alphabetical order and with a number first. So this will turn into 2xy plus 3. That is the partial derivative with respect to x. Now let's find the partial derivative with respect to y. So if I want to take the derivative of that first term with respect to y, this time x squared is a constant, so I'm going to write that first. And I'm just going to be left with taking the derivative of y, which is technically just 1. I'm going to move on to taking the derivative of this middle term. If I'm taking the derivative with respect to y, I'm treating x as a constant. A constant times a number is just a number, so the derivative of that is technically 0. And then finally, my last term, I'm taking the derivative with respect to y. I'm going to do this like normal because I don't see an x here. This is going to be negative 12y squared. So I do want to clean this up a bit. X squared times 1 is just x squared minus 12y squared. And those are my partial derivatives with respect to x, with respect to y. Now let's move on to part B. I want to find the derivative with respect to x first. So I'm going to take it term by term, just like I did in that last example. I'm going to start with the first term. If I'm taking the derivative or partial derivative with respect to x, y is a constant. So I'm going to go ahead and put the 3 and the y to the 5th first. Any part where I'm not taking or the derivative of it, I like to write it first. The only thing I have to do now, it's not what I wanted to do, is take the derivative of x squared, which of course is 2x. I'll clean it up in the next step. I'm going to move on to taking the derivative of my middle term with respect to x. So y is a constant. I'm going to go ahead and write 2y squared. So it's out of the way. And I just need to take the derivative of x cubed. The derivative of x cubed is 3x squared. I'm going to take the derivative of my last term. I am going to need to use the extended natural exponential rule. This is e to the x times y. I can't forget to take the derivative of my exponent. Remember, we're taking the derivative with respect to x. So y is a constant, and that is the derivative of my power, which is just y. Now, sometimes students have a really hard time with this. Think of this as if you had e to the 2x, where 2 is acting like our y. When you take the derivative of this, it's e to the 2x times 2, because that's the derivative of the exponent. In our case, y is 2. It's just some constant. Okay, now I'm going to clean it up. So again, the form that I want you to do in the activity, you will have your number first. So if I am looking at this first term, 3 times 2 is 6. Alphabetical order tells me I need to write x next, then y to the 5th. That's how you're going to have to do it on the activity for it to tell you are correct. I'm going to go ahead and clean up this middle term. This is a plus. 2 times 3 is 6. Alphabetical order, x will go next. It's squared. And then y squared. And then finally, the correct way to write this term is the y first, and then e to the xy. So all of this is the partial derivative with respect to x. Now I'm going to find the partial derivative with respect to y. I'm going to do this step by step, just like I did the last example. This first term, if I'm now treating x as a constant, I'm going to write my number and x first. That way I only have to worry about taking the derivative of y to the 5th power, which is 5y to the 4th. Moving on to the next term, I'm treating x as a constant, so I'll write 2x cubed first. Notice I'm not taking the derivative of that, I'm just getting it out of the way so I can take the derivative of y squared, which ends up being 2y. And then I want to take the derivative of e to the xy with respect to y, so this will be e to the xy times the derivative of my power. This time my constant is x, so I'm multiplying it by x. Cleaning this up, this would be 15x squared y to the 4th plus 4x cubed y plus x e to the xy. Please note the form, so when you move on to the activity questions, you will know the correct form for the activity to tell you you are correct. Okay, let's move on to part C. I want to find, of course, the partial derivative with respect to x and y. I am first going to rewrite this function because I see that I have variables in the denominator. I want to go ahead and bring those up. So I can rewrite this. X to the negative 4, y to the negative 5. And now I can find my partial derivative, so fx. I'm treating y as a constant, so I'm going to write everything pertaining to my constants first. So that way all I have to do is take the derivative of x to the 4th. The derivative of x to the negative 4th is negative 4, x to the negative 5. I can go ahead and clean this up. This is negative 8, x to the negative 5, y to the negative 5. It's okay to leave your exponents as negatives. If you would like to make your exponents positive, this is an equivalent answer. So negative 8 divided by x to the 5th times y to the 5th. Either one of these will work as your partial derivative with respect to x. Let's go ahead and find our partial derivative with respect to y. This time I am treating x as a constant, so I'm going to write all of my constants first. So then I can just take the derivative of y to the 5th, negative 5th, I apologize. This is negative 5 y to the negative 6 using the power rule. This becomes negative 10 x to the negative 4, y to the negative 6. Again, I can leave my answer like that. If I wanted to leave my exponents positive, this would be negative 10 over x to the 4th, y to the 6th. Both of these are sufficient. Now let's move on to example 4. A company sells two models of cell phones. They have a basic model and a luxury model. The demand functions for the models are given by those two functions. You will notice a subscript of B for the basic, and you will notice a subscript of L for the luxury, where piece of B and piece of L are the prices of the two models in dollars, and X is the units of the basic model sold per week, and Y is the units of the luxury model sold per week. They are asking us to find or determine the total revenue function. Now, in the past, when we were asked to find the revenue function, it was only in one variable, so we always just did price times x. When we have two variables, it's very similar, but we can't forget about the fact that we have another variable. So when we go to find our total revenue function, it is going to be price times x plus price times y, where again, if x is talking about the basic model, this is going to be a subscript of b, and y is talking about the luxury model, this is going to be a subscript of L. We can go ahead and plug in both of our demand functions, multiplying them by x and y respectively. So I can distribute x to all of these terms. Whenever I have a term that has two variables, write it in alphabetical order by the letter. So x will come before y. For the second one, I'm going to distribute y to all of these terms. Now that I have all of my terms, I am going to see if I can combine any terms. Those are the only two terms that we can combine, so let's go ahead and combine those. Everything else, I'm just going to leave it the same. I'm also going to write it to where I have the variables that only have one x or y first. This part, it doesn't truly matter the order of your terms. If I combine those two highlighted terms, I will have, negative 0.2 xy minus 0.15 x squared minus 0.15 y squared. Again, the order does not truly matter. This is our total revenue function when we have two variables. For part B, they want us to take the partial derivative with respect to x, and then they want us to evaluate it when x is 200 and y is 400, and then they want us to interpret its meaning. So I'm first going to find my partial derivative with respect to x. I will go term by term. Derivative of that with respect to x is just 160. My next term, y is just a constant, so the derivative of this is 0. Derivative of this term, again, y is just a constant, so the derivative will be negative 0.2 y. Next term, the derivative of this with respect to x, I bring down that power of 2 and multiply it by negative 0.15. This will give me negative 0.3x. And then finally, the derivative of this term, y is just a constant, so the derivative of this is 0. I'm going to clean this up. I don't really need to have the zeros there. I had them just so you can see the derivative of some terms would be 0. So this is 160 minus 0.2y minus 0.3x. Now I'm going to go ahead and plug in 200 for x and 400 for y. Y is 400. X is 200. So this will give me 160 minus 80 minus 60. Now I will show how I ended up getting this. If I'm going to multiply these two together, I'll do my work on the side. 0.2 is 2/10 times 400. I can get rid of a 0 and a 0. This leaves me with 2 times 40, which is how I got the 80. If I want to do this again, but for 0.3 times 200, 0.3 is 3/10 times 200. I can get rid of a 0 and a 0. This will give me 3 times 20, which is how I got the 60. Now continuing, this will turn up or end up being 80 minus 60, which is $20 per unit. That's going to be technically the units on this 20. Now we want to interpret. Now we are going to interpret this in a very, very specific way. When 200 basic models and 400 luxury models are sold. Now, if you're wondering how do we know the 200 goes for basic and the 400 is for luxury, they told us that in here. They told us X is the units of the basic model and Y is the units of the luxury model, looking at that last sentence. If the sales of the basic model increases by 1 unit. Okay, I'm gonna need to move this so I have more space. And put it there. And the sales of the luxury model stays the same. Okay, now before I move on to the rest of it, the reason why we write it this way is I'm saying the basic model increases by 1 unit because I'm taking the derivative with respect to x. If I was instead taking the derivative with respect to y, then I would say that the luxury model is increasing by 1. And then the other one that you're not taking the partial derivative of is the one that has to stay the same. So again, because I'm taking the partial derivative with respect to x, x represents the basic model. That's always going to be the one I say increases by 1 unit. And then the other one will stay the same. And in this case, the other one is Y, which represents the luxury model. That one is staying the same. The total revenue increases by the amount that we got. And it is approximately by the amount that we got. And this is how you would interpret what it means for our partial derivative with respect to x, evaluated at 200, 400 means. We're going to cover the second order partial derivatives in the second video. After you watch this video, there are a handful of questions for you to answer in the activity. Please make sure you use the same form that was shown in this video.